Hey folks, today we're going to talk again about precision. Precision of groups, measuring the precision of groups. And if you've been watching our channel for a while, you know that I use extreme spread quite a lot. In fact, a lot of folks use extreme spread as a measure of precision. I think extreme spread is a good measure of precision because it tells us an awful lot about how one load performed in contrast to another. In other words, it's pretty easy to compare apples to apples using extreme spread. But there are other ways to measure or estimate the precision of a load. And today we're going to dig into a number of those different methods. We're going to be using a software that I developed years ago called Ballistic. I don't really pursue its development anymore because for the most part there are other pieces of software that simply do things better. My application Ballistic doesn't do G7 ballistic coefficients, which in my estimation is absolutely required today. But one thing that it does do is it does a nice job of calculating various measures of precision, including extreme spread. So this is a group that I fired just the other week. I was off the bench, and this was fired from my Ruger precision rifle. It's a 5-shot group at 100 yards, calm wind conditions, and all I was doing is double checking that my 200-yard zero was correct. After firing these, by the way, I moved my Schmidt-Bender scope over 2 clicks to the right so that my grouping then came out right here, right where it should be for this 200-yard zero. But that's a whole nother story. So what we're going to do is we're going to be measuring the placement of each of these rounds. And to do this, we're going to harken back to our days in high school geometry or college geometry. And hey, do you remember the term Cartesian coordinates? Sure enough, right? So imagine that these are points on a graph, and what we want to do is, first of all, come up with the coordinates that describe these points. So we need an x-coordinate and a y-coordinate. We can do that with something like this. This is a graph that I developed for use with that Ballistic software. The Ballistic software is free, by the way. In fact, if folks are interested, I can post it on our Dropbox so people can download it and make some use of it. The only thing different about this graph is that it's sort of an inverted Cartesian coordinate type of graph, where our 0, 0 point is in the upper left corner instead of the lower left corner. The reason why I did this is because it's easy to translate these coordinates into what's called pixel coordinates on the screen when I was programming Ballistic. The 0, 0 point in the 0, 0 point for the screen pixel coordinates is in the upper left corner. So that's why that's just a little bit inverted, in case you're wondering about that. Now, looking at this graph, we have kind of some indices along the x and the y, 1 inch, 2 inch, 3 inch, and so on and so forth. And then that's broken down even further. We have 1/4 inch lines. Those are the more bold lines that you're seeing. And we have 1/10 inch lines that are a little bit smaller. So you'll see out to 1 inch here, 10, 0.10, 0.20, then the 25, 30, and so on and so forth. So with this in hand, this makes it a whole lot easier to acquire or create the coordinates for these bullet impact holes. Now, really the easiest way to do it would be if you have a digitizing tablet and you use your mouse or the puck and you click, 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 and you're done. But most people don't have that. I don't have that. So I developed this technique right here it's kind of slow. And it's kind of painful sometimes if you got a lot to do, but it's kind of interesting at the same time. So the process is where we're going to lay this here, and then one of the important pieces is we want to make sure that we place this grid in such a way that we don't wiggle it or move it in between the rounds that we're measuring. In other words, we don't want to call out a measurement for, let's just say, shot number 1 up here, and then accidentally we move this thing a little bit when we're measuring shot number 2. So what I'm going to do is I'm going to place this, and I'm going to note, and you could even tape this down, where my 0, 0 point is in relation to the little grid that's drawn on that target itself. Okay then. Shot number 1, we're going to start in that, let's say, the upper left corner of the shot group, and we're going to move in essentially in a clockwise direction. There's 5 rounds here. So the first one is at an X coordinate of 2 well, it looks like, I'll say, 2 point, I could say it's 2.1, but it's actually a little bit to the left of the 2.1 inch mark. So I'm going to go back just a little bit. I'll say 2.07 inch. And then the Y coordinate on this side is less than 1 inch. There's my 0.75 mark. It's greater than it. 0.6, or 0.8, 0.9. I'm going to go right in between that 0.85. Round number 2. Moved over here. Again, starting with our X coordinate, we're at 2. 2.5, 2.6, 2.60 inches. Now, there's no grid lines to actually allow you to do anything finer than 1/10 of an inch. So you got to kind of estimate a little bit, use your best judgment on that, be consistent. This isn't really rocket science. We're just trying to do the best we can to understand or estimate the precision of our rounds. And the Y coordinate for round number 2, there's our 0.75 line again, 0.8. That one I'm going to say is a 0.83. And I'm going to say that is a 8.3, maybe an 8.4, instead of 8.5, because I can see that the round impacted just a touch higher than the first round, which I recorded at 0.85. The third round, the third, fourth, and fifth are a little bit more tricky because they're nestled in right on top of one another, especially the fourth and fifth rounds. Well, I'm calling it the fourth and fifth rounds on how I'm measuring it. I don't recall the order that they were fired in. So round number 3 impacted at an X coordinate of 2 point, let's see, there's the 25 or quarter mark, 0.3. Let's say 2 point. It's not quite 0.4, so I'm going to say 0.38. And the Y coordinate is 1 point. That's pretty good right there. 0.20 where it fell. Now once again, there's our 5-shot group. and the overlay like this to read the X and Y coordinates from each. Then the resulting X and Y coordinates for each of those 5 rounds. All right, now that we have our coordinates written down, created for us, it's time to jump into the Ballistic software. This is the software I was talking about a little bit earlier. Now this has got a lot of different stuff available to you from the main screen. We don't really care about that. What we need to do is go to the Tools menu, and we're going to jump right to the Range Measurements Calculator. This is what this looks like. So we're going to put a little title in here to remind us of what we were doing that day. So this was, as I said, 100-yard group from the bench. Hit tab, and this was the 0.308 caliber. We had 5 rounds that we fired in this one, and the next step is where we jump down to inputting the Cartesian coordinates for round 1, and then we're going to click accept after each one. So round 1 we said was at a location of 2.07, hit tab, 0.85, hit tab again, we can accept it. Then we jump to round 2, 2.6, and notice it's prompting us for round number 2. If you got a lot of rounds and you have to stop for just a moment, you might get confused of which one you're entering, so it reminds you of that. Press enter. 2.38, tab again, 1.20, enter. 2.40, tab, 1.40, tab, enter. And now the last round, 2.60, tab, 1.50, tab, press enter again or accept again. And now we're going to display the group. And that looks awful similar to what we saw in person. The last step is where we click the Do It button. Go ahead and do these calculations. There we have it. Results of precision measurements for the .308 caliber 5-shot group. Mean radius 0.303, mean spread 0.803, extreme spread 1.147, median spread 0.776. Then it asks us if we want to save this group file. Yes, we do. And it asks us what we want to call this. So this is my .308 Winchester. I was shooting 168 grain Sierra tipped Matt King bullets. This is my reloads at 100 yards. You can be as descriptive as you want with this sort of thing. Now the next thing I want to do is I'm going to close the measures screen, go back to the main screen here, and now we're going to jump into the CEP calculator. This is the circular error probability calculator, and notice it's asking for a group file. And that's what we just created. So sorting it by date modified, I'm finding the round or the group that I just saved. I'm going to open that, and it defaults to 100 yards. If this actually wasn't shot at 100 yards, that's where this becomes important too, is you have to change this. Then we're going to go ahead and calculate circular error probable and a bunch of other things as well. So there we go, the .308 Winchester with the 5-shot group at 100 yards, telling us that 50% of the rounds will land within a circle that's 0.436 inches in diameter. 99% of the rounds will land within a circle that's 1.308 inches in diameter, and that this load is shooting sub-MOA 0.872 at 95% confidence interval calculated from circular error probable. Now what's very interesting here is this information coupled with this information, mean radius, mean spread, extreme spread, median spread. Now this gives us an awful lot of information about how well this group performed. Extreme spread there is 1.147 inch. Over here on the CEP calculator it says this load is shooting sub-MOA 0.872. So it doesn't use, CEP does not use, by the way, does not use extreme spread for its MOA calculations. So according to this, extreme spread was 1.147. 1.147. We multiply that by 100 and then divide that by the value of 104.7. That is 1.047 multiplied by the range in yards. Now here we see that we're just over 1 MOA when we use extreme spread for that calculation. So now we're darn near deluged with data. We have various different ways of looking at the precision of this round, and it's all good stuff. But all by itself, it's kind of useless if we can't compare it to another load that we may be looking at, or we want to just see how well we did one day or another. All right, well, let me set this up here. Now, what I did is I went through all the different groups that I had measured and calculated over the years. And what I found is that I had quite a number of different groups for the 7mm REM mag. Now this is a Browning BBR that I've had for quite a number of years. And so I have assembled 4 groups. Each of those shot at 200 yards off of the bench. For the most part, these are all 160 grain bullets, save for one where I was experimenting with a little bit lighter bullet, the 150 grain Barnes tipped triple shock. Now on this graph, what we have along the x-axis is a series of different measurements of precision, different ways of measuring precision. On the y-axis, we're actually looking at the actual measure of precision, and for the most part, that's inches. Now there's a couple of take-home messages we can glean from this graph. First of all, the values or the precision measurements that are closest to the zero, obviously, are our best groups. And regardless of how we measure it, the 160 grain Barnes MRX bullet did just a fantastic job in this rifle. But one of the take-home messages we can't ignore is the fact that the bullet that did the best has essentially a flat line across all those measures of precision. And that indicates that all those measures more or less agree that it's a good grouping. Now the second thing that we're looking for is differentiation among those different groups. If we have a measure of precision that doesn't differentiate one good group, let's say, from a bad group, then that measure of precision really doesn't give us much ability or power to make any sorts of decisions about those groups. And we kind of see that off on the left side there with that mean radius measure of precision. We also kind of see that if we're just looking at MOA. But the measure of precision that gives us the greatest differentiation is the circular error probable, CEP. But calculating CEP, as you saw, is kind of an elaborate process. What I'd like to draw your attention to, and the third point that I'd like to make here, is that extreme spread gives us pretty good differentiation, and extreme spread is very easy to calculate. So while a person can go through all of the steps that we went through today, you may not really be gaining much relative to the simple measurement of extreme spread. CEP is probably a bit more, perhaps more realistic, a little bit more conservative of an estimate. Is it worth all the work going through all that to make the calculation? In my estimation, it's not. I like using extreme spread. I can measure that out in the field, out at the range, and I feel very confident that I got a pretty good estimate of how this gun is doing, how this load is doing. And as we see here, it's really pretty much as good as any of the others. In fact, it's better than quite a few of the others. Well, thanks for watching once again, and stay tuned for some more videos we've got coming up in the not too distant future.